Okay, so for this question, it says prove or show that the real line with metric space with the metric the distance metric of x and y is equal to the absolute value of x minus y is a metric space. So first we have to know what the metric space axioms are as such, and so let's take the assumption x and y be in the set of real numbers such that x is not equal to y with the distance metric absolute value x minus y. So for part A, it's pretty trivially true. X minus x, or any number minus itself, is always 0. It's just a 0 identity. For part B, we can use a trick right here, x plus c equaling to y, because x is not equal to y, right? So there exists such a difference. And with that, we can substitute that in the function c that is equal to the absolute value of c. Since this is the absolute value of c, this is always going to be greater than 0 and not equal, or it's going to be always greater than 0 and not equal to 0 because c is not equal to 0. For part C, right here is just a simple switch. I am factoring out the -1 right here. This is just 1 right here, and you can swap it. This is just y minus x, which is the function of dy to x. For part D, it's a little more tricky, so we need to just unpack a couple of things. So yes, like let x, y, and z be in a set of real numbers. This is just the formula of what the distance of xz, xy to y and z are equal to. So we need to know very importantly that, for negative a, for this identity is always true, right? So basically, let's say like -1, right? -1 times -1 is going to be less than or equal to absolute value of -1, right? Which is just 1, right? Let's say, for example, 1, right? 1 is always less than or equal to absolute value of 1, right? That's just trivially true. 1 is equal to 1, but also 1 times -1, right? That's -1. -1 is going to be less than or equal to 1 right here. So that's just a quick example to convince you that this identity is true. And also you need to split up the absolute value function, right? This is just kind of how it's defined in terms of a sum, but this is just true if this is just like one value, which is just a plus b right here. So yeah, we have to split it up x minus z right here. Because this is just minus y plus y is 0. I'm just substituting it right here to try and derive a way we can substitute this to get what we want. And there's the first case is going to be when x minus y plus y minus z is greater or equal to 0, right? So this is like this. We know that this is this. So the function absolute value a plus b is just going to equal to itself. We don't have to change it at all because it's already positive, right? And since this is positive, we know that this value is always going to be less than or equal to this value, right? The absolute value of itself. And this is less than or equal to the absolute value of itself. And so, yeah, obviously, both of them being less than or equal to themselves grants it. And then I can substitute the distance functions right here. So this works for this case, right? Next case is going to be x minus y plus y minus z is less than 0. So right here, this is true because we know that this is less than 0. This is the case. So we can multiply this by -1 because this is going to be true for the absolute value function. And we factor this out here. And from here, right, we know that this again is true, not just for the positive case, but for the negative case as well, right? So then we can do the similar trick for here and see that's true. And so this is going to be true for both cases, thus making it true for the entire proof.